having. So this one is just the first part, and I believe you will be interested more also on the other parts that we will be discussing for the next couple of weeks. So I'm going to share with you today grid modernization, transforming energy systems level with model-based design. So my team have already give you some entry polls. So hopefully you can actually take participation so that we understand how we can address your questions and other things that we might be able to see, so that we are able to answer your questions properly in this case. So yeah, I guess the entry poll is coming up, so I can see some results in this case. So let's just wait for a moment and see how I guess this one comes up. So, okay, so most of you are more on the academic or research institutions, I believe, and some students, and then some are embedded developers. Okay, so I guess that one will be, how to say, we can address, hopefully, your requirements for grid modernization or grid design as we go through the webinar today. So let me go through my agenda for today. For today, I wanted to share with you some energy challenges that we are actually facing, right? So in a global energy challenge, there's a growing demand for clean and reliable and efficient electricity. And how does this drives the need for advanced technologies for electrification and power electronics. So another one is, how do we meet these challenges of electrification and power electronics? So we'll discuss more of the specific challenges you as an engineer, or maybe a student, or maybe a lecturer in the universities face, when we are researching or integrating renewable energy resources and design power electronic systems that are efficient and robust and safe. So in this case, we'll see how the role of model-based design in electrification will help in the development, and what are the key roles for model-based design in tackling these challenges by connecting the system modeling, simulation, control, and validation of this integrated workflow. And this workflow, what we call model-based design, how you go from system-level design and then deploy it or implement it and use testing within MATLAB and Simulink. And then finally, we'll have an overview of how we will be using model-based design in MATLAB and Simulink, particularly using Simscape as the tool to develop physical models in the environment. And you'll see how Simscape helps you to actually model electrical, also mechanical, thermal, and physical domains together. And we can provide realistic system representation of your grid implementation. So let's jump into the agenda, and let's see how we can help actually in this energy challenge that we are going through. So throughout this webinar, we will also have some demo of how you can use Simscape as a modeling tool for your electrification needs. So let me go through the electricity energy challenge that I was discussing earlier. So to begin with this talk, so why do we need to modernize our energy systems? Actually, this one is a very big challenge for engineers, electrical engineers like us. So first, we are seeing, number one, as we have known for a while, for some time now, that greenhouse or gas emissions globally are driven by continued reliance on fossil fuels, right? So, and electricity, because of electricity generation and transportation. So there's a critical meeting requirements that reducing these emissions, hopefully we can meet climate targets at the same time. So the demand for electricity keeps growing for electrification, for example, vehicles, expansion of industrial processes, for example, integration of renewable energy sources. So this adds to the complexity of the grids that we are seeing right now, which puts more pressure on, let's say, system stability or efficiency of the system. So in the middle of all these things, actually, you can see that electrical systems must handle all these evolving demands. So these systems include everything from generation to conversion and even storage. And to make this system smarter, more efficient, and really heavily on advanced electronic control designs. So this is where our software, MATLAB and Simulink, and with the special tool Simscape, may be able for you to allow us to model, simulate, and optimize the performance of the power electronics. Maybe it can be also motor drives, in this case, grid-connected converters, for example, for deploying them into hardware and then deploying it to our actual application. So the big picture is to address these increasing emissions and demand, and we need to design power systems and control strategies that are not only efficient but also flexible, reliable, and ready for energy transition. So let's take a look at this diagram that I have, what we have for traditional power grid systems, so which are structured maybe 20, 30 years ago. You can see that these are the legacy systems that we have seen. So in traditional grids, power generation is centralized, like coal, nuclear maybe, or hydroelectric, are produced at a high voltage, and they are transmitted over long distances for robust transmission systems. So these are high voltage transmission lines, for example, substations to step down, for example, the voltages. And like, for example, we have synchronous condensers to help manage reactive power and maintain stability. But as well, we can see now that there's a lot of changes in the modern grids that we see, and it looks very different from what we have seen previously with distributed energy resources, inverter-based renewables, for example, and bidirectional power flow, creating more technical challenge to the control. So actually, we can see the emergence of the following components that in the grid electrification. So for example, wind farms, solar panels, for example, solar farms, and including battery storage systems. We also see some hydrogen generation or storage systems, or the similar things maybe. There are also EV charging stations that we see every day that are being put up. And also maybe some of you have home EV charging if you have an EV vehicle at your home. And most of all, the emergence of high voltage power electronics that are now available in the grid systems. So these are the changes that we see every day in our electrification landscape right now. So let's see how we can help in meeting the challenges in electrification and power electronics, and what's the role of model-based design in electrification. We'll show you how it may help in tackling the challenges by connecting system modeling, simulation, control design, and validation in an integrated workflow. So, of course, power electronics control design has its challenges. These systems include a lot of complex dynamics and interactions. So efficiency, for example, and stability of the system are important. And so far, it should be safe operations and reliable in this case. So sizing of components for efficiency, battery behavior, for example, and degradation, controller tuning, which involves real-world operating conditions, embedded software. So we have to implement embedded systems to control or, for example, fault mitigate our systems. And then hardware software coexistence and integration. So these are just some of the complexities that we see, not necessarily in power electronics only, but on major electrification applications in this case. So what's the role of Simulink and model-based design in this case? So Simulink is the modeling and simulating the simulation environment for power electronics and control. Includes grid simulations that are enables a complete workflow. So simulating control algorithms, power electronics, and RCP, for example, rapid control prototyping, hardware in the loop testing, and generating codes for production applications. So these are just part of the workflow that is supported, what is dedicated verification, testing tools, and to meet the standards. So power electronics engineers have access to MATLAB's capabilities, plus the ecosystem of the software enables us to build solutions leveraging the capability of Simulink and Simscape in this case. So by using Simulink and Simscape, so engineers are able to simulate design and verify control algorithms, making errors easier actually to detect, or earlier on in the design, you are able to actually detect and correct your system behavior or your software before actually deploying it into hardware implementation. So let me just show you some examples of our customers that have actually used model-based design. So STEM was able to actually troubleshoot hardware problems using Simulink model. So during their hardware development phase, they were experiencing some problems that they could not pinpoint, for example. But using measurements and Simulink models, they were able to actually reproduce the hardware problem and in simulation, and then able to find the cause and correct the error. So this is just one example of a system in power electronics where we are able to help in accelerating the development of the system. This is because we are able to actually simulate a virtual example of your system, and then earlier on be able to check the errors earlier on in the design, even before you actually deploy your system. All right. So let's go through a little bit of how the model-based design workflow is, and how you go from system-level design to detailed implementation and testing using MATLAB and Simulink. So this is just a snapshot or an overview of how actually we are running the simulation as it becomes executable specification. So this lets the teams actually link, share, and a common understanding of the requirements. So these are essentially our requirements, right? It can be compliance requirements, or it can be customer requirements. So these requirements are actually essential in our design, so that it immediately impact any specification or design change. So that we start with simpler models actually, and then move on to more complex system dynamic iterations and see the multiple domains in this case. So what it helps is actually a multi-domain application for Simulink and Simscape, electrical, mechanical, and thermal applications. So these are just some examples of how we can link actually the requirements from our customers. And then from that, we do our design using the models that we have for physical systems design. And then from there on, we do the design and test for our, for example, control systems, supervisory algorithms, or control systems using simulations. So in this case, we are continuously testing the design even during the design phase, and then going through formal verification methods. So these are just some applications where you can use actually model-based design at the same time, model-based design and model-based verification through requirements application. So we have several applications that we have used with our customers that are, modeling and code generating capabilities. So in this case, for example, we are able to actually help one of the customers that, they are doing modeling and code generation capabilities, and actually they're using hardware in the loop testing with speed goat hardware for rapid control prototyping. So this allows their engineers to actually explore, test, control strategies. So without even actually have extensive codes that they have to actually write. So because of this, they are actually able to actually see in simulation, in fast sampling rate needed, about their controllers to be implemented in FPGA. So using this kind of applications, they were able to actually use rapid control prototyping that give them time to focus actually on the control design rather than writing the HDL codes. So these are one of the advantages that you can actually see with MATLAB and Simulink, compiled with together with SpeedGoat, for example, as a real-time testing solution in this case. So we just talked about how we can actually do desktop simulation using model-based design. And then we are able to actually do model verification in this case, while it is a powerful tool in the design. So uh, it is very powerful to get the control algorithms perform the same as with running a microcontroller or in a processor. So in model-based design, we are not only running it in our in the PC, in the workstation, but actually we are able to actually generate codes, C or HDL codes for FPGA, for example, from both control algorithms and the electrical models. So this gave you a real-time testing options. So you can actually generate real-time testing for control algorithms. You can hear what we call rapid prototyping as what I have shared earlier. So the code is implemented in this very real-time system, which is a deterministic real-time computer. So the second option actually for generating code for electrical systems model is known as hardware in the loop. So this hardware in the loop is actually helps us engineers to test our control algorithms not only in the model in the loop only, but actually you are also able to actually emulate the actual system, electrical system in this case, and test your systems so that you can avoid, building the hardware is actually is very expensive. So in this case, model-based design helps you to actually simulate an emulated system in your in Simulink environment. So this one avoids expensive damage, for example, in a case where we want to trial the controller systems in this case. So you can test the controller systems, put fault conditions in a model, and actually also you can actually also implement it in the real-time system and check how your system behaves within the control system itself. So these are just examples of how we can integrate our model-based design in this case to implement our control systems, but we are also testing real-time these components, these controls, so that we can actually verify it immediately. So one example of our customer that is using is this propulsion, for example, propulsion motor with a full-scale power converter. So I think this one is more of power electronics, control design, and embedded systems. So this gives us the capability to actually also do hardware in the loop testings for, in this case, shipboard, power electronics. This one is more of maritime applications, but this one is also, power electronic systems on large ships, for example, megawatt microgrids, powering propulsions and onboard equipment. So these systems require actually very big investments to build. So what they did is actually they did first in a model-based design environment, which involves MATLAB, Simulink, and Simscape Electrical, and then eventually they are able to actually test it out in Simulink real time with the speed with a real time system in this case. So which they used FPGA workflow using HDL coder. So this is an example of a model shipboard power electronics using hardware in the loop testing. So eventually, the last stage of model-based design is how do we provide production-ready code for power electronics or maybe energy management systems or for your grid controls. So it is through model-based design, actually, we can help generate fast and efficient code through autocode generation with Simulink. And besides implementing the code on a microcontroller, in this case, for example, this one that I am showing here, it can also be code generated from to an FPGA, for example, so that you can actually do software in the loop testing, for example, or processor in the loop testing to verify numerical equivalency of your code, of the control code in the Simulink model algorithm. So Simulink offers a path for this to perform actually several software checks. Software in the loop testing, for example, to run generated code and then control algorithm in parallel with Simulink testing. So these are able to generate your codes at the same time and put it in microprocessor, for example, and then you are able to actually check the responses of your system. So Simulink will step the processor for each time, for example, collect the output data, compare the differences, and again, verify the numerical equivalency of the control algorithms. So this one generates model-based design is able to actually help you to generate C or HDL code for implementing control algorithms on microprocessors, for example, or FPGAs, ASICs, that maybe you have ASICs application also for power electronics or electrification to conduct software in the loop, for example, testing, or processor in the loop testing to verify the numerical behavior of your compiled code. So this is just part of the formal code proving tools that Simulink and Simscape are able to actually provide the aids to ensure that the generated code is free from errors and developed with maybe compliance standards. So these codes, we are able to actually help certain customers to actually code their control algorithms on specification, specifically written by control engineers. So I think some of the control engineers may be hand coding algorithms or debugging hand code or handwritten codes, which is tedious and error prone. So I guess what Simulink and is able to help each one of the engineers is actually help to actually build the code, generating it from the Simulink models or the control models that they are already have. So the controller has been able to actually manage power and balance and share loads. So in this case, also fault detection has been implemented. Control algorithms has taken steps to actually cascade faults and maintain power delivery via all the blocks. So testing and debugging these control systems actually occur in the hardware, which is both expensive and dangerous. So I guess model-based design helps us to in a way, avoid those serious damage if not managed properly. So we need to verify their algorithms via modeling and then simulation before actually deploying it into the hardware testing. So these are just some examples of our customers that we are able to help in this case. So finally, this is actually the whole view of model-based design for power electronics and electrification in general. So model-based design is actually based on using a system-level simulation. So there's a system-level simulation or maybe a requirements from system level. And then you have a dynamic behavior of the system. So you have models for this, and then power of the power electronic system. So we link together all the requirements. In this case, so continuous testing is actually very important earlier on the design for each of the following changes. So because actually all throughout the design phase, our requirements may be changing. So in this case, we are able to actually test while we are even developing the system. So there are tools that help you to actually develop and verify your control systems, signal, for example, processing algorithms. So this helps us reduce the time for testing embedded software for your control by generating code from the model itself. So in Simulink, you have a control model. So actually you can see and generate the codes from these models. So also to meet uh, compliance requirement. So this helps us also in certifying the codes to industry standards. So if you are familiar with the V model in most of the safety systems, so actually, model-based design is actually based on something similar of that scale, where every system starts with requirements, and then these requirements we are able to actually design a model. In this case, a simulation model in Simulink and Simscape, and then from there on, we are doing actually testing, continuous testing of our model until we are able to actually be very sure that our model is actually meeting the codes for industry standards. So these are just one of the many applications of model-based design in electrification and grid modernization in this case. Yeah. So we've spent some time actually to describing model design to you. So model-based design is actually a proven way to develop embedded code, control codes for your design, and help you actually test your systems. Oh, sorry. Test your systems that are not always practical or safe, or maybe you need a very big hardware. In this case, for example, grid applications or renewable energy applications. So you have a very big hardware to test, which is actually very expensive, or it requires a lot of investment in this case. So what we usually do is we usually use model-based design to help develop our plant models, and then eventually develop our control algorithms to control these systems, electrical systems. So from there, you can actually test your codes in ways that are, can catch design mistakes earlier on in the development process. Where it is still less expensive to correct because they are still in model-based design. So all of our customers' references that I've shown earlier tell the time actually most to save using model-based design. So it happens because of a journey they took to change how they develop embedded software, for example. And first project using will take a certain amount of time as their current approach, right? And this happens because they are learning in a new way to do something. However, if we continuously use model-based design workflow, if you can see that much more time goes into our design and simulation and less time actually testing and retesting or building hardware, and which lessens the cost actually. So they begin to realize the time savings for subsequent projects, for example, and experience the confidence, for example, in beginning to reuse the models from previous projects, which are actually related, maybe, for example, power electronics or electrification or grid design, and find the greater transparency in their design by writing and reviewing codes as generated from the models itself. So actually, these are just the basic applications of model-based design in electrification and how we can actually modernize our control systems using model-based design applications. So using MATLAB and Simulink, so we can actually show how we can develop our physical models or physical modeling environments. So we have Simscape to develop actually model of electrical systems. It can also be mechanical or thermal and physical domains together, providing more realistic system representations. So let me just show a little bit of how we use Simscape as or MATLAB and Simulink in this case for different approaches in dynamic modeling dynamic systems. So if we have the models, or what we call first principle models in this case, so we have physics equations, right? Today we are talking more of electrical systems, so we have the physics equations for our electrical systems. So we usually use Simscape and Simulink for modeling. But sometimes our models, we see that, hey, why our model is not meeting what we can actually see in the environment or in the actual system. So we use system design optimization to actually parameter tune what we have on the first principle models. So in this case, we are able to actually match the simulation to meet the actual representation of our models through parameter tuning with Simulink design optimization. So this is just, these are working hand in hand together for our system to be actually accurate in the modeling of our electrical systems. But sometimes if the system is too complicated, maybe we can use system identification to actually model our system. But for today, we will focus more on Syncscape as a tool to help us actually in modeling our electrical systems, like, for example, grid applications, microgrid application, renewable energy systems, battery systems, in this case. So let me give you a little bit of an overview of what Simscape is able to actually help us in rapidly creating models or physical models within Simulink environment. So with Simscape, actually, you can build physical models based on physical connections that are directly integrated within the blocks. So Simscape have these blocks or building blocks that I can show you later on that are, model paradigms. You model the systems, for example, electric motor. So you actually don't use the equations itself. So the libraries or the models already have built in the physics of those for example, in this case, electrical motors or bridge rectifiers, for example, or any mechanical systems by assembling components. So in Simscape, we are actually componentizing these systems in order to model certain parts of your electrical systems. So this is an add-on product that you can add to model complex components and analyze capabilities. So Simscape helps you to actually develop control systems and test system level for performance. You can parameterize your models using MATLAB variables and expressions as you always do in MATLAB or Simulink, and put it in as an application in Simscape, and then design your control systems, in this case, to provide physical systems to Simulink. And then later on, you can actually deploy these models, for example, in your hardware in the loop systems. So Simscape actually supports C code generation for you to be able to actually deploy in hardware in the loop testings that you actually do within your testing capabilities. So I just go through some Simscape features. So Simscape offers a comprehensive environment physical model, providing wide array of blocks. In this case, physical domains such as mechanical, electrical, and hydraulic systems. In this case, so beyond the standard model, so Simscape actually empowers you as the users to create actually also custom components through a dedicated Simscape language. So you can actually also have a custom made um, a model for your Simscape use. So the diagram also on the right actually includes is like an hydraulic servo valve created in Simulink Simscape. So in this case, this shows that this diagram on the right is actually the flow of how we are actually using Simscape during our model development from requirements, and then implementing it through our integration and testing. So this is because Simscape can be actually code generated to enable users to actually test embedded controllers in a simulated environment. All right, so maybe let me show you how in Simscape Electrical, there's a lot of libraries that is available for us to use. So in this case, for example, if you are working on electric today, so we have generators and motors, transformers, lines or FACTs, converters or electrical drives. So these are just some simple applications that actually you can use for your systems application. So let me show you a little bit of how we can actually see Simscape within the Simulink environment. So here I'm actually showing the Simulink environment. So Simulink actually is a visual or more like library-based modeling where you can actually place certain libraries for your system. So for today, actually we will use more of Simscape in this case. So Simscape have different types of libraries. So if you are just having the Simscape function, actually you will only get the foundational and some utilities. But if you are actually developing battery systems, for example, you can actually get Simscape battery to help you actually develop battery systems. And actually this includes also battery management systems controls. If you are developing EV or mechanical systems, you can actually use driveline or multi-body systems. So if you are also in some thermal analysis or something like that with fluids, you can actually use Simscape fluids. But today, we will use more of electrical systems. In this case, we will use semiconductors and converters in our demo later on, and then maybe some control systems that we can use for three-phase systems for very high power systems. Actually, there's a specialized power systems if you want to use. Actually, this one are used especially for that applications. In my case today, I will show you uh, uh, e solar panel application with inverter application. So those are what I can show you today. So if you can see here, there's a lot of electrical systems libraries that are available for you to actually have. So there's already ready-made control systems that you can use, and then parameterize, and then later on parameter estimate so that or tune so that you know it it meets your requirements. So it also works with electromechanical, with motors, PMSM, reluctance stepper motors or synchronous motors. It also have some functions for integrated circuits, for example, or passive components, definitely. And then semiconductor devices, and then the specialized systems that I was talking about, where it has the control systems also, power grid applications, power electronics, and sensors. So these are just some of the applications that can be used for Simscape applications. So what are the applications of Simscape Electrical for your use? So number one, you can use it actually for your systems design. You are able to actually determine certain power requirements, for example, or you have system level response, so you can measure your efficiency. Another way, you have component validation, for example, where Simscape is actually able to, you can actually put information or parameters within your system, and then parameterize those datasheet specifications, and then actually meet your switching dynamics, for example. And then you can also actually do component design. So you are able to actually, for example, calculate losses during switching events, for example, or analyze or predict fault behaviors. So actually in Simscape, you are able to actually provide some kind of fault analysis for your simulations and see how your system behaves. So that one removes the dangerous testing, for example, in actual physical systems. But this one actually provides a test for you to be able to do it in a virtual environment. So I think those are some key points that I want to share to you, so that you know you are able to actually develop those electrical systems in this case. So yeah, so model test control systems within electrical. So these are just what I'm showing here as a workflow actually. So your models can be actually converted into C code. It can be auto-generated code, and then enables you to, so from your physical systems, you can actually generate the code so that it becomes a virtual environment. And then you are able to actually deploy your control algorithms in a processor, for example, in this case, a processor in the loop, and then virtually doing the testing. So in this case, for example, processor in the loop, and which is PIL. And then later on, once you have some confidence on your control algorithms, you can eventually transfer to hardware in the loop testing, where it will be your plant code or your physical system can be converted into a real-time system. And then you are actually interfacing with your control systems through hardware in the loop, where you already have the controller systems that you have. So this is actually just one example of a workflow where we are able to use Simscape Electrical to develop your plant systems, and then eventually together they are forms uh, your control systems, which examples are energy management systems, for example, or battery management system to control, or power electronic systems control to control your physical systems. Physical systems can be motors, your grid, your solar panel, for example, and all these things. So those are the applications that we can show. So let me show you an example of a solar panel, a solar power inverter application. So actually this one is also available online in this case. So let me show you an example of this solar panel. So this solar panel is actually from the solar panel. So there's a DC voltage coming out of this a solar panel. And then from this solar panel, actually, we have an inverter. So from DC, we convert it to an AC, which drives the grid, a single phase grid. So you can see that we can later on, we can generate the powers, the voltage and the power from the solar panel, and then eventually get power into the grid. So let me show you this example, and then maybe one by one we can do the parts. So let me show you how we can easily actually drag and drop the system, for example. So in this case, this is the block of the whole system. So we have a solar panel application block, and then we just have a capacitor to maintain the voltage, and then we have an inverter. So from the DC voltage here, we are actually driving the output to an AC grid application. So let me show you how we can actually easily um, pull out, I mean, use pre-built library from Simscape Electrical to provide the, let's say in this case, solar panel. So in Simscape Electrical, we have a sources panel. So with this, we have a solar cell library. So let me click and drag that application, I mean library. So when you have this library, actually you can double click it, and then there are certain parameters that you can actually update from this model. So actually from here, you can actually select some selected components already that are parameterized within MATLAB and Simulink, which is available uh, in Simulink itself. So these are libraries you can use to, for example, just an example to get, for example, you are using commercially based solar panels. So you can also use this application. So you can select the components, but there is also already a parameterized um, parameters that you can actually use eventually. So for example, these are the cell characteristics initially for this solar cell. And then let's say we have a series connected cells of 700 components. So you can actually parameterize your components in this case. So you are actually eventually putting up easily how you can actually provide the panel configuration for your solar panel. So let's say we are having this kind of operation. Then we have two parallel solar panels, for example, to integrate with our system. So let's connect it properly. So this connection is actually through your irradiance connection. So this provides the energy to the solar panel. So later on, I can show you that connection in this case. So, okay, and then okay, so now we have a connection for our solar panel. So now we have this panel. So the input to the solar panels is actually the irradiance. So this is the amount of energy, solar energy coming into the solar panel. So in this case, this is just a constant value. This is, I think, 1000. So this is just the initial value, for example. And then we have uh, a, four quadrant converter is like a bridge rectifier. So we can actually populate, for example, four FETs so that it drives the AC signal, or I mean the AC power to the load. So in this case, we will use Simscape electrical semiconductor components, where we will use an N-channel MOSFET in this case. So let me pull that one out and then see what you are able to see. Yeah. So now we have this application. So you can actually also double click it, and then you can actually change certain modeling options. I think this one are for depending on your fidelity that you want for this model. So let's say you have a drain IDS current for this case, let's say 15 amps. So these are just certain values that you can actually change, or you can get it from the specification data sheet specification of your favorite MOSFET, and then put it in this parameter page. and then we can use it for our simulation. So we just connect this one to the gate, and then the drain, for example, and then the source, and in this case, the emitter. So internally, there's a driver already that we have provided in this case. So these are also Simscape electrical components in this case. So let's just add the MOSFETs to drive this model. Let me just show you this one. Okay. Okay. So now we have two. I think we need a little bit for four of them. So let's say like this. Control I. Okay. Okay, let's connect this one here. Okay, and then so here. Oops. Yeah. So this is just an example of this circuit where we are able to actually generate AC signal from application from a solar panel application. So now we have this simulation ready. So let's try to run the application. So we can actually view the system response in this case. By the way, this one has already a control system designed initially before, but you can actually provide the control system simulation also for this case. So let me just show you how this simulation works, and then let's try to run the sim. Yeah, so you can see that the DC voltage from the solar panel is about 350 volts. And then we have a demanded power, or 20 AC, 20 ampere AC RMS. And then we can see actually the AC sign voltage about 220 volts peak to peak. And then this is the AC current application. So this is just one example of simulation from solar panel application to AC application. So hopefully this demo helps you to actually have simulations that we can actually provide for you. So there are a lot of already ready-made applications within MATLAB itself. So actually I can share some of you. For example, this one on the GitHub. So there are already ready-made microgrid, for example, microgrid applications that you can use. This one is a microgrid application with Simscape. So you can actually use these applications for your microgrid applications, for example, or other high power systems. So you don't really have to start from scratch. Hopefully these kind of examples are able to help you to actually build the components that you need for your grid simulations, and then eventually your eventually your control systems applications. So you can actually download this one. I will provide this one later on in the link or the handouts that will be provided later on. So yeah, so to end our webinar, I'll just go for some key takeaways that, physical modeling helps to bridge actually the gap between theoretical design and hardware design, and integrate those simulation circuits and controls to help us catch the design flows earlier on in the system. And then actually Simulink environment help us to actually offer a digital twin environment to convert our design and to optimize it. And then we have shown you also today that there's an end-to-end workflow that enables simulation, testing, verification and validation, and then code generation, and eventually hill testing, and finally for your hardware deployment. So thank you very much for listening. I'll take you back to our marketing team. Thank you very much.